Hey everyone! Today we're going to talk about frequency response and a little bit of the math behind it. So frequency response happens when you have a periodic input, like a sinusoidal input, and are at different frequencies. So this is going to require a slightly different analysis than we've been doing, but we could still use our Laplace tables. All we need to think about though are the real conditions and the imaginary conditions. So we're going to think a little bit on the terms of physics with a lot of this. We're going to have magnitudes that are going to be important, and we're going to have ratios that are important. And behind all of that, we can do it. So with this in mind, we can think of a standard input like the sinusoidal approach, where maybe our actual x of t function is like a sine wave. So a sine wave would have some type of a times sine of wt, where this is our amplitude, and this is going to be our frequency. So amplitude is measured out in standard terms, but our frequency is going to be measured out where W is 2 pi over P, which is going to be the radians per time because that's based on 2 pi over the period that it takes to go through that 2 pi. And that's also equal to 360 degrees over the period as well. So period could be a T, it could also be a P, whatever you might prefer. I'm primarily going to use a P for period because I think it makes a little bit more sense, P for period. So if we think about the Laplace transform though of this expression of a sine Wt, if we go to our Laplace table, we're going to get out an AW over S squared plus W squared. So we still have our W terms in here for frequency, and we also have our amplitude term in here as well. So with that in mind, we can then potentially see that whatever this g is, it's going to actually transform x into y. We have some direct relationship where g of s, we know it's going to be y of s over x of s, and thus y of s is g of s times x of s, as we've been using throughout this course. But for whatever g of s is, we need to make sure that's going to actually be a stable term. Now, the good thing is this can be relatively stable throughout the class, but we're going to focus on primarily highly stable conditions. So we know that x coming in is going to be this sine function. The y output is going to depend on g for sure, but it's also going to be based off of whatever x is that's actually going in. And so we're going to walk through a little bit of that throughout the course. So today, we're going to start off with an example, and that example here is going to be, what if, let's say, if maybe, oh, I'm right outside the box. If perhaps g of s was a single first order function like k over ts plus 1, then what might that look like? Well, if we plug that in directly, we would get from here, y of s is k over ts plus 1, and we already know that x of s is aw over s squared plus w squared. So we could go ahead and actually do the multiplication of this, and then we can go ahead and do partial series fraction expansion. And based on the partial fraction expansion, we could go ahead and do the inverse Laplace. But fortunately, this is actually already in our Laplace tables. So based on our Laplace table directly, we know that this has a unique solution of, if I do the inverse Laplace here, y of t is equal to k a w tau e to the minus t over tau over 1 plus w tau squared plus ka over the square root of 1 plus w tau squared times sine of wt plus phi. So phi in this case, or phi, whichever you prefer to call it, is the arctan of minus w tau. So this is our phase shift. And then what are these two pieces? Well, the first one is going to be called our transparent response. So the transparent response is going to be the automatic initial response that we're seeing from it, and then we have ongoing oscillations. So we have the transparent response, and then we have ongoing oscillations. that will continue to persist. And so this makes sense from a standpoint that we could do the math on the inverse Laplace to get to this, and that we have two pieces, especially because of the fact that we would be able to expand this using partial fraction and get multiple pieces from here. But we need to actually consider what this looks like and what this means for us, because this is going to still be an actual periodic response. So while we haven't written it out yet, this will have its own periodic response as well as our output. So how do we relate the both of these to each other, and what are we doing to look in between them? So when we consider how this might look laid out, let's draw that out for a second and do a little bit of analysis. So let's say that this is my time, and this is my, let's just say output. It could be x of t, it could be y of t, it could be really anything. And so let's say that I have x of t here. Wow, that's a very nice one. I don't usually draw so well, so that's pretty good. And then we're gonna have a y of t function like this. And I'll make sure to write out y of t, and the first one is going to be my x of t. So when we think about the analysis of how we got from here to here and actually plotting that out, let's think about it for a second. So our very first term goes to 0 as t goes to infinity. So that is true. As t goes to infinity here, this entire term is going to go to 0 because e to the minus infinity is 0, therefore the first term will be 0. So the ongoing oscillations there, we need to consider what's going to be happening. So if t goes to infinity, then what does that really mean for us in describing the first versus the second term? So, well, the second term has some frequency as its actual input that we're going to be noticing, and that's because the sine times wt plus phi. So this specific term for the ongoing oscillations part should definitely have given away a little bit of what our output should look like, and that we do have that to be true. And so we have some contribution from the transparent and a contribution from the ongoing oscillations, where the ongoing oscillations involves this sine term with this new amplitude in front of it, this Ka over the square root of 1 plus Wt squared. Our long-term response has a different amplitude and a different phase, though, than our actual x of t function when we go from x of t to y of t. Now, in this case, I've more or less written out the amplitudes to look similar, but we don't actually have to make sure that they are similar. We just want to look at the ratio between those amplitudes. So overall, we do have a generalized function out here that we are looking at for our function y of t. Our y of t for our frequency response, so y f of rt, is actually more or less, in this case, the amplitude of the new sine of wt plus phi. Where again, this is going to be my phase shift, the arctan of that minus wt, and this is my new amplitude. So a hat versus my original amplitude, a. So let's think about some of these conditions. So we have some type of time shift happening between these, meaning between these two happening from here starting versus here starting, that is some change in time, or a time shift. The amount of time it takes for the response of the system to actually then yield a y of t as it passes through our g of s transfer function. That delta t, though, directly is equal to minus phi over w. So this would need to then be in radians, where phi could be in degrees, but if phi is in degrees, then that needs to be multiplied by pi over 180 degrees. And then this can be plugged in directly for this system. So if that's now true, then we could plug this in where sine of wt plus phi with the a in front is now a sine of w times t minus delta t. And that would be true. All because of this relationship of delta t as it is. Whereas we see this delta t times w is equal to minus phi. Thus, a minus of those is a plus of that. And we already have a plus of that in there. Therefore, we can substitute that in directly, and we would have WT minus W delta T, pull out the W, and we have W times T minus delta T. So that expression is absolutely true. So when we look at a new term like the amplitude ratio, our amplitude ratio is going to thankfully sound a lot like it is. The amplitude ratio, or AR, is going to directly be the output amplitude, I'll just abbreviate it as amp, over the input, I almost read output again, input amplitude, which is A hat over A. But we know that for a first order system, we can actually kind of see what that amplitude is, because if we actually take those pieces out of what that is and divide them, then more or less for a first order system, what is the ratio of the amplitudes of my output over my input? Well, we know what our input amplitude is, it's just A, and we know that our output amplitude is A hat. So if we take the full output amplitude and divide it by the input amplitude, what we're seeing is Ka over the square root of 1 plus Wt squared over A. So what's left? Just K over the square root of 1 plus Wt squared. And that came from this piece divided by this piece. So when we think now about the phase shift a little bit more, I've already written it out in a couple of different ways, but this is entirely true based on its period. So if we know that this is true, like this term and this term, where we're saying, okay, well, phi must then phase shift, that if we know that this is equal to minus W delta T, and that is definitely true, we also know that this is equal to the arctangent of this system. Oops, I'm so sorry. I forgot the minus. I was like, something seems off. I'm pretty sure that's supposed to be a minus. There we go. The negative arctangent, yeah, because of that, of, in this case, W tau. And that's also based on this relationship where we have to do where phi is also equal to minus delta T over the period times 360 degrees. And that's because that is true where W is this. So if W, this term here, is equal to 360 degrees over the period, then we've substituted that and multiplied that by the delta T. But we also know that in this case, the phi is also equal to the arctangent negative of WT. That's where the minus actually came from. Okay. I was like, I definitely wrote that incorrectly. My apologies on the incorrect writing. So in this case, this is entirely true as well for describing our phase here and how we're looking at this to be true based only on the time shift. The time shift and the actual frequency of the response are directly related to the term the phase shift. So the shifting of the phase of our system as it progresses over time. So based on these that are true, we can see different conditions that might actually change out based on how we might adjust the frequency, the tau term for our residence time. We might think about adjustments to the amplitude ratio. All of these will be true for a very fast or slow changing system. So if that's actually happening here and we want to consider that, then we're going to consider two quick responses here. And I'll put them right in the center. So let's say that we have the input is changing quickly. What's going to happen to the output of our system? Well, if the input all of a sudden starts changing very quickly, then 1 over the frequency is going to be much, much less than tau. And so why would that necessarily be true? So a very fast changing frequency means that this W is going to end up being really, really, really fast. So therefore, it's going to be high. By fast changing system, it's going to have a very high frequency or W. That 1 over W term then is going to be super small, especially compared to the original tau of the system in general. And thus, we can essentially state, in this case, if we multiply W by both sides, that 1 is much, much less than tau w as well. And so the tau w term comes directly here into our arctangent term here for our system for the phi. And so if this is true, then this will end up becoming phi is, in this case, equal to the arctangent of course, w tau, will now be approximately negative 90 degrees specifically. So it's a complete adjustment to our system. For the amplitude ratio, though, this is going to end up being k over the square root of 1 plus wt squared. But that wt term, where the w is quite large, is going to end up becoming directly much greater than 1. So because wt squared is going to be a very large number and is going to be much greater than 1, this becomes k over the square root of wt squared, or k over tw. And that will directly end up being our system, where the amplitude ratio is now just based on that. However, if the input change is slow, then in this case, when we look at the 1 over w, this is going to be much greater than tau, because now the frequency is very low, and thus w is going to be very small, making this a very big term. So in that case, 1 is going to be much greater than tau w in this situation. So if that's true, and we have a very large arctangent value, then my phi, the negative arctangent of this large value, is going to be approximately equal to 0 degrees in this case. Furthermore, my amplitude ratio, that k over the square root of 1 plus tau w squared, well, that term is going to be very small and approximately 0. So it's really just going to end up becoming k over the square root of 1, which is just k. And so in this case, a very slow changing system will look different. And so what does this mean for us? Well, if my input value for these, I'll mark these as like A and B. In A, my input looks like this, and my output looks like this. Notice that they're very different. I don't want them to actually start off at the same point, but notice that they're very, very different. It's because it's quickly changing, it's quickly adapting. A for my input is going to be very different from A for my output. But in B, notice that my phase shift is going to be 0 and my AR is going to be K. So if my amplitude ratio is about K, whereas 1, they're going to end up looking almost identical. And that's because over time, my output is going to ultimately try matching my input. And as my input changes slowly, that means that my output has a time ratio to catch up and maintain consistency. And so this is definitely a lot of like general explanation, but what we're really trying to do here is identify that we might have inputs that are having some type of amplitude and frequency for these periodic inputs, and that our transfer function, as long as it's stable, can help to dictate through this transparent ongoing oscillation term. We could then see the relationship of x and t and y of t based on our amplitude ratios and our phase shifts, and we can use those to see what happens if the input change is fast or if it's slow. So next, we're going to think of more of a shortcut method to approach these frequency response problems. So as before, our output is equal to the transfer function g of s times our input function x of s. And we know that x of s is going to be this input function of the sine term with this amplitude a. So in the Laplace space, that's AW over S squared plus W squared. But we can actually factor out in the bottom, where would be the inverse of the foiling, for S plus JW times S minus JW, where the J is our imaginary term I. So J and I, either or, whichever you prefer to use. And so if we take the inverse Laplace of this for any possible situation, and this really is anything, we would then assume that all potential situations involve distinct poles, repeated poles, complex poles, and the contributions of our input here. So our distinct poles and our input contributions are definitely going to be the, let's say, simplest way of looking at this. But in reality, we really only want to consider this where we have our real of our AI terms. So any of those A terms up here, actually then truly being less than 0. And that's going to be because of two reasons. We want to have a system in which g of s is actually stable, and truly we want to consider where as time goes to infinity, the terms that will not decay to 0 will remain and hold true. And so those are actually going to make these the preferential, where we're going to be considering where terms decay as t goes to infinity, and we want the real of our a of I terms to be less than 0 for stability. We then get our frequency response function as essentially d1 e to the minus j wt plus d2 e to the j wt. And so in this, we have essentially done a partial fraction expansion to get to here. That's more or less what we've actually done by just placing this highly generic system. And I mean, this is as generic as it comes. Truly generic for any possible situation. So how would we solve for d1 and d2? We can use a direct substitution method where we would actually then substitute directly for, let's try ds, where s is equal to plus or minus jw. So if this is true, we can consider the situations in which if and what d of 1 would then become. So back on the previous, when we think about what this actual expression is over here, for thinking about it, how would that system actually look? Because that does need to justify that it came from that kind of position. So d of 1, more or less, would actually be in a situation where we would have our y of s with our s plus jw term that's emerging from here, because again, this is really saying that we're doing a partial fraction expansion on this specifically. And so the partial fraction expansion would assume that we're going to multiply everything by that. So in this case, I'm kind of skipping a step here, but we're really just taking this to be where this is equal to minus jw, and then d2 is equal to y of s times s minus jw at s equals positive jw. But again, where would I have gotten that from? Well, back in the day when we did this, we can multiply by either of these two situations. So we can essentially say if y of s times s plus jw would be equal to multiplying s plus jw on both sides. And this would give aw times gs over s minus jw. Virtually the same, y of s if I multiply by s minus jw on both sides, then it cancels out here, leaving me with aw times g of s over s plus jw. And so that's really all that we've done here. So we're now just substituting in for the potential condition of d1 at where s is equal to minus jw. So if that's the left-hand side, then the right-hand side of this expression for that specific term would be aw times g of s over s minus jw, but s is minus jw. So s minus jw. That's aw gs over minus 2 jw's. Well, those w's will cancel, and we'll just get minus aw over 2j times g of s. And that works. Furthermore, for d2, we would consider the opposite condition, because really this just tells us two potential conditions here, where this case is going to be for the s minus jw one like this, and this is going to end up being for s equals jw. And now again, this is just based on our partial fraction expansion or direct substitutions. Either way, they allow us to solve for the potential of d1 or d2. So here, that would then be aw times g of s over s plus jw. Well, s is jw, so jw plus jw is going to be two of those. So we're going to have our a w g of s over 2 jw, which is aw over 2j times g of s. And so really it's just the positive form of the other, where now we can see that d2 is equal to d1 based on the negative. So a negative d2 is equal to d1, and that holds true here in this situation. And thus, if we wrote that back out for this term here, we can then say, and I'll change markers to go back into that regular expression, that y frequency response of t is d1 e to the minus jwt plus d2 e to the positive jwt. And so hopefully that should give some intuition on where those came from specifically. So notice that the d1 was at minus jw. That's because here, this would have been s for both of these if we had done that return. So ultimately what we've really done here, based on this term here, that's where that truly comes from. We just substitute for what that s would have been by direct substitution. But in this case now, we've actually solved for what those are. So y of FRT is equal to the d1 term, which is going to be minus AW over 2J G of S e to the minus JWT plus AW over 2J G of S e to the JWT. And in this case, that holds true. But this S term has now already been substituted. So really, this is minus AW over 2J G of what the S was, minus JW e to the minus JWT plus AW over 2J G to the JW e to the JWT. And that is true. Where again, this is G of S, that's e to the ST, G of S, e to the ST. We can make that performance evaluation and assume that to be true. So then what is? The question should remain, what is G of JW? What is G of negative JW? What do those mean specifically? Well, the G term of our transfer function does need to have a real and imaginary element to it, because we need to think about all the potential cases where that J is in fact talking about the real versus the imaginary. So G of JW is actually equal to the real piece of G of JW and my imaginary component piece, which is the imaginary term times imaginary, G of JW. So in reality, we could just call that R of whatever term that we want, like W, and J times the imaginary of W. Because in reality, the real of GJW is going to just be based on W, and we already know that this is going to be based on RG, therefore that's true. Furthermore, we can think about the magnitude-based ultimate expression of this term, where G itself, for whatever G is, needs to be evaluated based on its specific magnitude of the expression and its elements of its real and imaginary planes. So we can write out this to be true based on our phase. And so where am I getting this from? Well, if we think about the actual how this looks in the real versus imaginary planes, we've had discussions about stability using real versus imaginary. But let's say that we have some specific function of my transfer function, G of JW. So G of JW has to have some contributions in the real plane as well as the imaginary plane, which in this case is the X and Y respectively. So my phi, or my phase change, is going to be the actual degree off the real that we have. My magnitude of G is going to be the actual amount of which it goes. And so we can solve directly for these terms where we know that the magnitude is going to be the square root of R squared and imaginary term squared, because we know that the magnitude of anything is going to be the square root of the X squared contribution and the Y squared contribution, where this is R and this is I. So then the magnitude of that is equal to the square root of R squared plus I squared, just like C squared is equal to A squared plus B squared, and thus C is equal to the square root of A squared plus B squared. Same principle from trigonometry. Furthermore, we can also see that the phi term that we get from this expression in total would be, in this case, the arctan of my imaginary over my real, for the same reasons from trigonometry. When we think about those expressions, in this case, our tangent, so we have the SOH, we have the TAH, and then the TOA, or the CAH and then the TOA. So the T is the opposite over the adjacent, our opposite over our adjacent. Arctangent then becomes the principal of that component of the imaginary and the real. And so in total, we can see that we can then describe this as the g function for the magnitude multiplied by the amount principled from our cosine or our real term plus the imaginary term times the principled from our imaginary system, the sine here, which means that this is essentially the same thing as this. They match pretty well equivalently. Furthermore, we can use Euler's formula to make it even a step further, where Euler's formula is going to essentially say that g is equal to the magnitude times j to the phi. So, or to the j phi. And that this expression will be true, which funny enough matches back here pretty well in addition. So based on all that to be evaluated as true, we can even do a little bit more math here. And what I want to do with that is plug this back into this expression and see what our total actual evaluated expression for y is, really for any transfer function that is stable or even moderately stable. So I rewrote the board to mostly focus on what we really have learned and gotten to thus far. So we said that y of s could be evaluated as g of s times x of s, where we've already solved that x of s is going to be our oscillating input function, and we've stated conditions that the real of which has to be greater than 0 to make it stable, and we're only considering the terms at do not decay to 0 as we go to infinity. So we then stated that the output y of t for our frequency response could then be based off of these two pieces. We solved for d1 and d2 specifically, and we found that ultimately this could be true for any stable transfer function g. So we have our g term, which is going to be based on our minus jw, and our g term based on our positive. Something I didn't mention is that our complex conjugate, this would essentially state that g of minus jw is equal to g hat of jw. Complex conjugate for this system essentially just means that you can state it as which to make them both of just jw and that you have a relationship between them. But that's just if we wanted to use it. We don't necessarily have to use it for the expression, but we have a lot of pieces here. We know that this is true. For really any stable transfer function, this statement will be true to describe our output. It's based on two pieces. We also know that Euler's formula that we just solved for states this is true, where we can have its magnitude and its phi, or the phase, that will help us to identify what the system will actually then look like. So from here to be true, and we know that this is actually then true, this is really interesting because we can actually plug these terms right back in and solve for a more shortcut approach. So I said shortcut. This really will be a shortcut. It just, we have to walk through the math to make it clear for the theory proof. So now doing that, having this to be true, we could substitute this for our specific terms, where g of ij can now be solved for in here, as well as g of negative ij. So in this case, y of FRT will be negative a over 2j, and I'm just already going to pull that term out for just a second here from both of these. We'll have our g of negative jw. So if we actually plug that in for here, that would then end up just being the magnitude of g e to the minus j of, in this case, phi. I keep saying of that to be true. That is definitely true for phi. We just are evaluating this, multiplied by e to the minus jwt. Now this, we pulled out the negative from here. Because of that, we're going to subtract the next piece. Negative of, we already pulled out the a over 2j. So g of jw is just going to be e to the j phi times our magnitude term. So I'm going to go ahead and pull that out of the expression too. So both of those have their own magnitude of g term that I'm pulling out of the expression, times e to the jwt. And so I'm going to make negatives all negative. So I'm going to put the negative back into the expression. And we're going to group a couple like terms here. So I'm going to go ahead and say this is equal to a times the magnitude of g all times e to the j phi e to the jwt minus e to the minus j phi e to the minus jwt all over 2j. And that this is true. I've put the negative back into the expression, and I've also already taken out the magnitude of g from both terms, and this is true. I can group these exponent terms together, actually, and when I do so, I'm going to get y f of rt is equal to a times the magnitude of g times e to the, pull out the j, wt plus phi minus e to the j wt plus phi all over 2j. And this will then ultimately be true. For any magnitude of g and phi that we get from our imaginary and real from the actual g transfer function, this expression will be true. And we can use this as a shortcut. But that's still not that short. There is actually a slightly shorter approach in how we actually can evaluate this term. So this is actually equal to sine of wt plus phi. This is just the much longer way of writing sine of wt plus phi, actually. So that makes this entire statement, in reality, fully y fr of t is a times g sine of wt plus phi. And that's it. For any g, all we need is to think about the input amplitude a, our magnitude of the g itself, our w for the frequency, and the phase shift that's created by the transfer function to form our output, which we also can solve for on the same two terms of I and R. And that's it. And why is this true? Well, let's think about this. A and G. Well, G and A, if they come together, G is the amplitude ratio. And that is equal to A hat over A. So A times G is equal to A times A hat over A. It's just A hat. It is my new amplitude, my output. That is the output amplitude, which is this. And phi is the phase shift of that. And so remember we talked about the fast versus slow input changes? This is what that means. Is essentially it's saying, how does that affect the amplitude of my output, and how does that affect the phase shift of my output based on those changing W's? And so am I generating a new output function, or am I staying ultimately the same? And that is something we can now do. And so how do we solve for this directly? Well, we know that to get this amplitude ratio of g, it's based on the square root of r squared and I squared. So that's going to be the square root of those real of the g function and the imaginary of the g function. Just like the same here for my phi term, that will also hold true. And this is my shortcut method, smile. We love smiley faces. That's true. That's absolutely true. So we can use this. Let's try an example. Let us use this example where perhaps g of s is going to now be 1 over 10s plus 1. And let's say that this is true. Well, currently this is not in JW notation. We need this to be in this oscillatory based notation. So in order to get g of JW, well, we'd want to solve for where s is essentially JW. So if we evaluate for this to be true, then 1 over 10 JW plus 1, that'd be true. But we don't really have a way right now of breaking that into its imaginary and real component. So let's attempt to do that. Let's multiply both sides by some type of factoring term to help with that. Maybe minus 10 JW plus 1. And so the top piece of this, g of JW is equal to minus 10j plus 1 over, well, let's do the multiplication. 10 JW times minus 10 JW is going to be minus 100 j squared W squared. but j squared is equal to the square root of -1. Square root of -1 in that term will help us with that expression as well. But ultimately, that then means that that will be -1. If j is equal to square root of -1, j squared is equal to -1. -1 times -100 is 100 times w squared. And multiply the next, plus 10jw minus 10jw is 0, plus 1. On top, we still have our factoring term here. It's just 1 times both, creates. So now we can separate this into a real and imaginary component. G of jw is going to be then, my real component is 1 over 100 w squared plus 1 minus j, or if I need to, I can keep that as a plus term, either way, and make this minus 10 over 100 w squared plus 1. And so now I have my real and my imaginary components of this term, which will both be true. Oh, I almost forgot my w there. Oops. There we go. Wouldn't want to forget the w. And so this is true, where now this is my real of gjw, and this is my imaginary of my gjw. The j term is there. We just have our real plus our j times our imaginary piece. And those are the two terms that we need specifically. Now, we don't actually need the j anymore. It's just more so a figurative element to help us to identify which component of which is the real and which one's the imaginary from the total complex base solution. So now that we have these pieces together, we can plug them in directly for our phi term and our magnitude term. Those are the two pieces that we need to actually solve this out now. So my phi term is going to be the arctangent of my imaginary over my real. That's the arctangent of my imaginary piece here, minus 10w over 100w squared plus 1 over 1 over 100w squared plus 1. Those two terms will cancel. This is now the arctangent of minus 10w, which is, solvable. In reality, we can leave it right now just as that, and that's fine. But if we had a w term, we would know that to be true. Next, we can solve for my magnitude of g. It is the squared root of my r squared, so my real component squared, 1 over 100 w squared plus 1 squared, plus my imaginary term squared, minus 10w over 100 w squared plus 1 squared. And so this, in that sense, we can then see how these can be broken up into distinct pieces. We can apply the square to the top and to the bottom of both of these two pieces directly. And ultimately then, we can solve this through and find that this is ultimately equal to the square root of 1 over 100 w squared plus 1. And that this happens to be true. So that is my amplitude ratio. That is my phase shift. And both of those can be used to solve through directly for my y, fr of t, in this case, which is a times magnitude of g times sine of wt plus phi. So in that case, that's going to be the whatever amplitude that I actually have for my input function, multiplied by the square root of 1 over 100 w squared plus 1, multiplied by sine of wt plus phi, which is the arctangent of minus 10w. And this expression is true. Fun. That is a more direct way of solving based on this solution. And that is true. So based off of this, we now have a pretty unique way to solving these more directly, and we can then see visual representations of these next and how we can actually approach looking at these solutions. And we are going to walk into even more complicated ones next. So let's talk a little bit more about this arctan function that we had. So in our continuing conversation about frequency responses, here we have a plot of our imaginary over real ratio against our phi, which is the arctangent of that imaginary over real. And so here we're looking at the outward response of what really is happening here for our r term. So if our r term is positive then we're going to be using this inward function for our arctan. But if r is less than 0, then we're going to be using these functions, where when it's actually true that phi would be then here, and my IR term would ultimately try and become 0, we'd be approaching either pi from the left-hand side or negative pi from the right-hand side, where there would be that asymptotic curve that we'd want to be looking at for those functions. And so why is this relevant and what does this mean for us? This is trying to help us to describe visually what's actually happening here for our phase shift. How is the phase shift contributing to the changing contributions from our input becoming our output through the transfer function g of s? So many g of s's will have their own way of then spelling out for us what's happening from the real and the ratio of the imaginary to the real and how that influences. So let's walk through a couple of potential examples. Let's say that we need to calculate AR and phi for the following expressions. So if we had, for example, g of s is equal to 4s plus 1, well, we would want to then find always g of jw first, which is 4jw plus 1. We automatically conceal the real and the imaginary terms from this, where our real term is first and our imaginary term is second. So we know that imaginary over real is going to be 4w always, for whatever w that is, 4w. And the arctangent of that is going to then become that I over r expression, or the arctangent of that to be true as well. So my amplitude is then going to be AR is equal to absolute of g. Real squared is 1 squared plus imaginary squared is 4w squared. That's going to be the square root of 1 plus 16w squared. And that is true. We also know that the arctangent function, phi, of 4w over 1, or just 4w. And so based on this, what are we learning about it? Well, we're seeing that r is positive here. R is a positive value, so we're going to be using this inward-based function here. And we're looking at what's happening here on this term of arctangent of 4w. Let's say that IR term, 4w over 1, where w is maybe positive. So in that case, that IR itself is going to be positive. It's going to be over here. And we know that the arctangent function, if that is positive, would allow me to then say, okay, well, the arctangent of this is probably going to be, if it's positive here, then it's going to be somewhere on this side where this would then be true. And so from our former example, we had g of s was 1 over 10s plus 1, where then we found that this was 1 over 10wj plus 1 when we evaluate for s equals jw by that direct substitution method. So from here, what we found was ultimately my absolute of g was the square root of 1 over 100w squared plus 1, and phi was equal to the arctangent of negative 10w, and that was true. So in this case, what we see is we are looking at the minus 10w inside. So based on that, we know that IR ratio is going to be negative for these positive w's. So it's going to be over here. But based on this to be true, we can also call this minus arctangent of 10w, which means this is a phase lag. So if these are phase leads, these are phase lags. And that's something we're learning about the situation here. We can also evaluate based on other expression terms. So perhaps we next are going to have a new one, which will be g of s is equal to 1 over s. Therefore, we're evaluating for g of jw is 1 over jw. How would we solve that? Well, we're going to multiply as we would by minus jw for both. This will then be minus jw over minus j squared w squared. That minus j squared is equal to just positive 1. Therefore, that's going to be over w squared. We can take out a w term from the top piece and the bottom piece directly. But either way, what we're really looking at here is 0 plus j times minus w over w squared. because there is a zero term there for the real that is actually true and happening. We have this j that we can evaluate and pull out, and we have this. We can express out one of these w's. We get 0 plus j times minus 1 over w. So our real term is in fact 0, and our imaginary term is minus 1 over w. So we know that the absolute of g is going to then become real squared, so 0 squared, plus imaginary squared, minus 1 over w squared. That 0 will go away, the square root of a squared will go away, we get minus 1 over w. And we are also then going to see, oh, my apologies, that square root of that is going to make that a positive and then square root, so that's just 1 over w. And then the phase is the arctangent of my minus 1 over w over 0. So that, in particular, is going to be division by 0. That's going to be a very, very large number, and that very, very large number is going to be equal to exactly minus 90 degrees, and that is true. That is exactly the case we talked about before, where we saw what happens if we have that w be really, really big or really, really small. And in this case, we're talking about that w term going to become extremely small, almost to the point of being 0, where that makes the phase shift automatically minus 90, which will be true. And we can even talk about another example where this term, g of s, will be equal to e to the minus s theta. So a time delay, basically. On that, we would then say g of jw is equal to e to the minus jw theta, where this can be evaluated directly in its cosine and sine terms as it is in e to the negative term base expression, where that will have a corresponding cosine of w theta minus j sine of w theta. That comes from the negative here, as we are just evaluating essentially for blanket minus s equal to some a, where then we're looking here at cosine of a theta plus j sine of a theta. We pulled out the negative because of that negative there, and that makes this the real term and this the imaginary term, where now we can look at my absolute of g as the square root of this squared plus that squared, but that's the square root of cosine of w theta squared plus sine of w theta squared. That is directly and consequently equal to 1. So r squared plus I squared, 1. And my phi is going to be the arctan of minus sine of w theta over cosine of w theta, which is equal to the arctangent of negative tangent, because sine over cosine is tangent. So we're really just saying the arctan of tan of negative w theta. I'm sorry, well, that is true. The negative w theta becomes negative positive here. My positive and negative sometimes get a little confused, but it's okay. So the arctangent of negative tangent just ends up becoming negative w, and that's because originally I had the negative in here. That's because that is true. We can pull the negative out directly from the expression, where then this becomes minus w theta, and that would be true. So all of these together are just showing us that for many different transfer functions, we can use the shortcut method pretty directly to solve through what might be happening. But there is a more complex transfer function that we need to consider, in which we no longer have first order systems, but we go into second order systems. So let's say that we have a second order or more complex. What about more complex g of s? Well, in that case, that's okay. G of s, let's say we evaluate it as the combination of many different transfer functions, like GA of s times GB of s, so on, over G1 of s, G2 of s, and so on. How would we evaluate the magnitude of G? How would we evaluate the phi? Magnitude of G will be the magnitude of each piece. And so I still have that S term, but I'm just going to ignore that because it will really be a JW term. Magnitude of G ... over the magnitude of those. and so forth. It is a multiplication of the magnitudes directly. For our phi term, that's going to be equal to the contributions overall of g of a plus the contributions of g of b plus the minus contributions of g1 plus the minus contributions of g2 and so on. We're adding together all those because those would end up becoming up here to the negative, and those then could be used directly. So in all reality, we're really just saying phi is equal to the phi of GA plus phi of GB minus phi of G1 minus phi of G2 and so on. And that's how you would use them directly in solution. Pretty fun. We can now take really complex systems and break them down into their component pieces and solve them directly using our shortcut method, where all we really need to do each time is find the absolute and the phi. Really, we're just looking at triangles. And we're just saying, okay, if this is G, this is my phi, what's the components of my real and imaginary? And then how do I use those to get both the magnitude and the phi? And we can evaluate those. Pretty fun. So I'm gonna go ahead and I'm gonna erase the board and write out an example. And then we're gonna use something called a Bode plot to try and walk through a more convenient graphical representation of how we could look into frequency responses. Here, we're now gonna have an example of our more complex system. So we're gonna have 3s plus 3 over 10s plus 1 times s plus 10. And we're going to try and evaluate this based on its total expression for g of s. So remember, we can break this up into numerator terms and denominator terms. So we can actually extract this 3 from the top and have 3 times s plus 1 over 10s plus 1 times s plus 10. Because we want the notation to always be something times s plus 1 or ts plus 1, we have that for at least 2 of those. This one, though, we can get by dividing everything by 1 over 10, or multiplying everything by 1. So in doing that, we would then now have 3/10 times s plus 1 over 10s plus 1 times 1/10 s plus 1. And that would be able to extract it directly from there. So in this way, I can rewrite this, though, as 0.3 times s plus 1 over 10s plus 1 times 0.1 s plus 1. So back when we were originally doing these expressions, we can find out which of these would be the limiting one and which would not. That can then go into the exponent. But either way, we can perform this as its initial operation. So why is this valuable? Why is this important? Well, because we see 4 distinct pieces here that we need to work with. So we can break those into their distinct components, and we will, where we will have the numerator, GA of s is that 0.3 plus j times 0, meaning that when s is equal to jw, I'm already trying to substitute a little bit into there to then extract out my real and my imaginary terms. My GB of s equals jw is this term, s plus 1. So then that's s plus 1 or 1 plus jw. Therefore, I have my real and my imaginary term. Here, I have g1 of s, which is 10s plus 1, which will be 1 plus j times 10w, and g2 of s, which is 0.1 s plus 1, which is 1 plus j times 0.1w. And those are my 4 component pieces. So from each, we want to consider their own magnitudes and we want to consider their own angles or phase. So for that, GA is the square root of 0.3 squared plus 0 squared. That's just 0.3. GB, square root of 1 squared plus w squared, square root of 1 plus w squared. G1, square root of 1 squared plus 10w squared, which is the square root of 1 plus 100w squared. G2, square root of 1 squared plus 0.1w squared is the square root of 1 plus 0.1 is 1/10, so square root of that is 1/100th, or 0.01 w squared. We could also look at those angles, so phi of GA, or you can just use this component based form, like this angle based. And then we have phi of GB, phi of G1, phi of G2, all of which need to be solved. So this is the arctangent base expression. So my arctangent of my imaginary over my real, imaginary term is 0 over 1, and that's going to end up being true. That means it's going to end up being 0. This arctangent of W over 1 is just arctangent of W. Arctangent of 10W over 1, and arctangent of 0.1W over 1. And how do we put them back together? We need a G total, and we need our phi total. So G is going to be equal to GA times GB over G1, G2. That, based on these, is 0.3 times the square root of 1 plus w squared over square root of 1 plus 100w squared times 1 plus, or the square root of 1 plus 0.01 w squared. Multiply through. Super cool. And then our total phi is going to be our phi for GA plus phi GB minus phi G1 minus phi G2. That is 0 plus the arctan of W minus arctan of 10W minus arctan of 0.1W. Another way to write this, if you'd like, is arctan of W plus the arctan of minus 10W plus the arctan of minus 0.1W. Both work, and both are true. And that will allow you to look at the total solution. Pretty fun. One last thing that we might ever consider doing is we might want to look at the log 10 values of my AR, which is the log 10 of my total G expression. And we might want to look at the log 10 values of phi. Those are going to be useful for us as we try and consider some straight line approximations in something that we're going to call a Bode plot. So a Bode plot helps us to determine break and critical frequencies that are going to determine stability criteria for our systems that we have in this oscillatory-based condition. So by looking at these log 10 plots, we can end up looking at straight lines. And so if we're looking at maybe log 10 of AR versus log 10 of our W plots, those are going to be perhaps different. So say that we have our AR plot or our log 10 of AR plots, and we're going to do those against frequency. And we have log 10 of phi against frequency. Those are going to be different than looking at just AR or frequency based on our phi and our AR, where AR is the amplitude ratio or our absolute of G. And we're going to be using this to determine a couple of interesting things about these plots. So we're going to see for some straight line approximations that we might have how we can start off with steady state values of interest and look into contributions of poles that are in the left-hand plane contributing based on the negative 90 degrees all the way to the positive 90 degrees. And so we are going to now walk through a little bit about Bode plots and what I mean by this, because these are related to Bode plots. To finish out for the day, we're going to talk about Bode plots. So Bode plots are more or less just a visual representation of all the contributions of the frequency as we can determine through our amplitude ratio and our phase. So in reality, these are just frequency response plots for our AR and our phi that are against W. So where W in this term is going to be radians per time, but our ARN value is not going to be that, nor is phi, which is actually going to be degrees. So we are thinking about degrees against radians per time in some capacity, but these are really just log-log and semi-log plots. So semi-log x specifically in this case. So we're going to need to get that log 10 of our amplitude ratio, and we want to try and normalize that to make this a lot easier in its value. We're also going to need our phi expression, and we're going to need to consider the log value of our frequency, which we can also do based on t, so we could also do log 10 of wt. So we're going to need to normalize ARN first. To do that, we're just going to normalize it by the gain, and that's going to lead us to just this expression. So everything, in a sense, is truly in terms of TW, as we already know how to get phi by now, which is also based off of TW. So let's consider some extreme conditions to the plot. Let's assume that WT is much, much less than 1, so essentially approximating and going towards 0. Well, in that case, our normalized value for AR is going to be 1. And that's because that is normalized, and that is, we want that to be 1 as its maximum normal. And ultimately in that case, when we think about this here, as this value goes as super small, that value is greater, so this becomes 1 over the square root of 1, or just 1. Additionally, when we think about the log 10 of that, log 10 of 1 is 0. So then, in this case, when we plot this out, that would end up becoming 10 to the 0 or 1, but ultimately when we think about the log plots, those are going to go towards 0 at that point. So then here, if we do the opposite, then those values are really, really big and much greater than 1. So in that case, that's the square root of TW squared, or just TW. Therefore, because it's 1 over that, it's 1 over TW as such, and we can then take the log 10 of that by doing minus log 10 of W minus log 10 of tau. Because this should hopefully be a constant, we can then pull that out of the expression, and we're really just looking at that changing with that as the intercept. So I'll call that the intercept here. So the intersection of this would happen then at WT equals 1, which makes that a really interesting point to consider, is when that's true, these terms must end up being equal, and that would make sense based on this happening. So the breakpoint then is what we would call that intersection value, or the cutoff frequency, because this is all based on frequency for our x-axis. And that's when the slope for our ARN is going to go from 0 to -1. So notice that here the slope is 0, and then here the slope becomes -1. So where that point happens is we're going to take a straight line and move it out. We're going to take this line and move it out as well. And wherever that intersection point is, that must be based on my WB, or my breakpoint. So these are directly aligned. These are using the exact same x-axis at the same time, so we just place them one over the other. And moving that directly down, we notice something unique, where WB also ends up being exactly at minus 45 degrees. This is this phase change point where this happens to be true. That's also true as WBT will equal 1 at that point. As WB is 1 over T in that case, we could see that to be true. Ultimately, this is a composite function. So what we're really trying to gain from this and the understanding here is what happens at low and high points for this system, where at very low we're a phase shift of 0, at very high we're a phase shift of 90, and how this makes a lot of influence into our system. So remember, a slow changing system has the time for our output to catch up. That's going to be over here. A fast changing system will be all the way over here. So we can determine stability criteria of our system over time based on the speed at which things are changing and how this happens. Pretty cool. We can also use our expressions to build out Bode plots from our direct poles and zeros. So a couple of key features. If we're in a left-hand plane pole, the slope will decrease in here by 1 for every left-hand plane pole. The slope will increase here for every left-hand plane 0, so different. So remember, left-hand plane poles are very different than left-hand plane zeros. Something important to always consider. Additionally, our phase diagram here below This one has a minus 90 degree contribution for every left-hand plane pole. That means it's going to end up at the end of the day 90 degrees down over here. But we're going to move up and shift up here by 90 degrees for every left-hand plane 0. And so remember, zeros and poles are different. Zeros are in the numerator, poles are the denominator. So for that example we had before, where we had, for example, a second order denominator system, and we had an S up here and we had two different S's down here, we had to consider the zeros that were based on the top and the poles that were based on the bottom, and how that would influence the design of this. But we can build it. Because a composite function here is a sum in the log space, we're really just thinking about a composite of frequency as it's expanded from here and here. So we can actually build that just by summing the terms together. So if we had contributing pieces of, say, we had one of these was down by 90, and another one was down by 90, but we had one of the zeros up there that would add 90, then the total of that would be minus 90. We just sum them together. We can actually plot them out and then make a composite mixed function like here in the green. And we could do the same here as with adding the ones above or subtracting the ones. Slope will increase or decrease by those and the left-hand plane pole or the left-hand plane 0. So hopefully this is a fun way for you to consider this. We're definitely going to be using Bode stability plots. And in our next lessons, we're going to be discussing stability criteria in these systems and how we can use this to design really advanced control-based systems. So hope you had a good time, and I will see you soon.